Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, everybody. I'm here. I'm pleased to be able to introduce Miguel Nussbaum. He's here visiting us from Chile, where he's a researcher at Pontificia Universidad Católica de Chile. Miguel has been working with us for, 5 to 10 years now, developing innovative education technologies. He's worked a lot in collaborative technologies, and most recently with working with our multi-mouse toolkit and creating something that he calls one mouse per child. And we recently won a LASER grant, a South American Research and Innovation grant that we also contributed to. And he's here to talk about old work, new work, and future directions. So without further ado, Miguel.
Thanks a lot, Donald. Hi. It all started 2006, as Kentaro just mentioned me, when I met Kentaro in Berkeley in one of the first, it was the first conference of ICTD, where I discovered that they had made a driver that allowed you to connect more than one mouse to a computer. And I saw there a wonderful opportunity to lower the cost of what we were already doing in collaborative work with Pocket PCs at that time. So what we did at the beginning was porting the software we already developed for doing small group collaborative learning with kids in one computer and 3 mouse. The idea basically was that these kids could work together inside the classroom, so it would really transform the classroom experience in such a way that the kids are the first actors in the classroom, those that really are working, and the teacher and mediator for those kids that need it. What we saw is that for this type of activities, the kids really collaborate, interact, and coordinate their work. What we lost from what we have done with Pocket PCs wirelessly interconnected is the eye contact, because the kids were looking to the screen and they were not looking to each other as they were doing before. However, for these small kids, they gained a lot because, as you will see here, they had a common space where they were working on. Before, they had their own machines. Now the machines were simulated by 3 individual spaces, so that the kid that had the blue mouse only could work in his own space, the blue one, the red on his own space, the red one, and so on. And there was a common space where the construction of the solution was done. Before, this construction was done in the virtual world, where everyone had a piece of this. So this focused the attention of the kids and improved learning. What we're doing now in the same direction with doing work like this one, where you construct, the idea here behind was that you have to order objects. The kids add pieces of this object that had to be ordered in an ascending way. We do the same type of activities now, but for language learning. Our idea was, what happens if we add to one machine 3 phones with the microphones, and instead of having individual learning of languages, we have a collaborative learning of languages. And the idea here behind is the following. Each kid, as you saw in the film, has a set of objects. In this case, the yellow one has the words day and party, the red one are and birthday, and they have to coordinate and synchronize as they did with the numbers, so to build the correct phrase. But instead of clicking to the objects, what they do, they have to speak. So for example, the yellow one touches a button in the keyboard, so the system says, your turn, you have to talk, and he says, day. And if the system recognizes that they was spoken adequately, they is accepted. Afterwards, this guy says, I want now, because it's they are, and he says are. However, it's not spoken adequately, and the system says, did you mean are? What's important is that this feedback is not only heard by the red boy, but also by the other two. So the other two heard how the red boy said R and what the feedback was. So there's a collaboration in the pronunciation between the guys. So they're collaborating not only in how to construct the words, but also they're collaborating on how to really speak the different words. What we found out, what's very interesting here, you have a photograph, you see the three kids looking to the screen, working together, and here you have the collaborative work, and here you have the individual work. What we saw here, these are the differences between the different groups. This is the collaborative one versus the control group, which was a teacher with no technology. Here's the collaborative one, where the both with technology, one collaborative and the other individual, and this is the individual versus the regular teacher. And what we saw that the significant differences were mainly in listening, because there was a difference between using and not using technology compared with control. And on the other side, there was a difference between the collaborative with technology and without technology. So we saw that there's an improvement because the collaboration really allowed the kids to pronounce better the words. So they learned to pronounce better the words. So there was a real improvement on working collaboratively in this 1, 2, 3 environment. I think I have again the wrong presentation. I am sorry, but I have again the wrong presentation as before.
Something about that presentation you really like.
Yeah, let me go again. It's the same problem I had before, exactly the same. I say that cannot be. I'm sorry about that. Okay, let's continue. Then we ask ourselves, how can we introduce games into this type of environment? And we have done a lot of work in games, but the most interesting one is the usage of first-person shooting in this type of environment. You say, how can you use such a terrible game as Doom for teaching kids inside the classroom? So what we did here, the kids have to order numbers, and what they do, they have to move in a maze and find the numbers they are assigned to, and then they have to capture or kill or whatever, let's say capture the numbers once they know the corresponding sequence. So for example, here you have 23, here you have 19, here you have 5. So each kid owns a number, and the kids have to capture the numbers in the correct sequence. So it's the same idea as before, but instead of being just sequencing number, we have the idea of first-person shooting, where the kids have to find the numbers and then select the corresponding numbers. We have just made the usability analysis of this game. We haven't done the experimental work yet, but we will begin this in late March. The school year starts in March in Chile. These are the photographs when you did the first usability analysis. Then we said, how can we teach science in such an environment? And what we did was Coulomb's law, what you have here, and the addition of forces. What you have here is the three kids. This is one kid, the second, and the third one. And here you have the electric charges, where they can select if it's how much positive or how much negative their charge is. And the aim is to move this electric charge, considering their position, which they can move, considering their positions, and move this charge towards this portal. The problem is that they have asteroids here, and they have to take care that the charge don't collide with the corresponding asteroid. So what you do here basically is you play with your position and the amount of charge, so playing with the different forces until you really move this asteroid here. And then different difficulty levels, so it starts very simple and can get very, very complex. And we did a comparison study to see how important it was, the immersion in such a game. Here it's important to notice that the pedagogical rules are intrinsic to the game rules, because the game rules are basic Coulomb laws. So if you really understand Coulomb laws, you can solve the problem. So to really make this work, you have to understand Coulomb laws. Here, you have the same rules, but now you have a narrative. You have a story, you have an environment where this occurs. And we wanted to understand how important the immersion aspect was in such a game. Here you have a movie where you see these boys working on this game. You have two groups here, 3 kids. Oh, I'm sorry, I shouldn't do that. I'm sorry about that. There it is. So you see how concentrated they are while they're playing, and they're really collaborating.
At least they had fun.
They had fun. And what's interesting is that there were 30 kids, and if I'm not wrong, 3 of them independently asked us where they could download these games. And the games was Coulomb law, so that the gaming rules were Coulomb's law, and they really enjoyed it very much. So the numbers we got were the following. What was interesting is that we have the game where you have this virtual world and the narrative, and the non-fantasy game, and there was no statistical difference between both numbers, and there was no difference between boys and girls at the end. So what we saw is that if the rules of the game are real, the pedagogical rules, and you can build the game with your pedagogical rules, you don't need really a fantasy behind, because the game really merges with the pedagogy. However, it's not so easy to bring up such a game. The trick is, how can you build such type of games? Yes, that's a game that did Alejandro.
Oh, okay, cool. Was there a baseline condition where they didn't play a game at all and they just had conventional study?
No, we just compared, in this case, we compared both of them. No, the idea was really to see, we didn't have a control group there. Then comes the phones, which I already said. Then we move to 1 to 10. In 1 to 10, it gets a little more complicated, because now you need a projector, you need a computer, and you need the mice, better said, and you need also the hubs. Our experience, and that's a hint, that if you're going to do things like that, I recommend the D-Link. The D-Link hub is for us the most reliable hub. If you're going to have 40-something mice, you need very reliable hubs, because it's very cumbersome to find out where your problems are. And the D-Link is very, very reliable. On the other side, you also have to do it in such a way that you're sure that your cables are not going to disconnect, because you're going to have trouble in the middle of, because the kids are going to move and the cables cannot disconnect. So you have to have it wired in a very intelligent way. Here's the 1 to 10, and the idea here is that the kids really collaborate within them and with the virtual world. Let me go here, and with the virtual world. So that's really important. That's the collaboration between the kids and the virtual world. And the idea here behind was to bring World of Warcraft into the classroom. That was really our motivation. World of Warcraft was 4 years ago a big issue. It is not as today as it was 4 years ago, but we studied what is really World of Warcraft. And World of Warcraft was first a game where hundreds of thousands of people interacted and worked together, collaborated together. And we said we don't really need such massive participation. We really want only the kids of the classroom to participate. We wanted multiplayer, we wanted collaborative, and we definitely don't want it online. We want it happens in the same place, collocated people. So we, instead of having a massive multiplayer online game, we transformed it into a classroom multiplayer presential game. And what we did, we first did a game for la cadena alimenticia, for, nobody speaks Spanish, for cadena alimenticia, for I'm so tired, the herbívoros, the animals that only eat the vegetables.
Herbivores.
The herbivores eat vegetables, the carnivores eat herbivores, and you have to have an equilibrium in the system. That's what's the name of this, the food chain. The food chain. The biggest problem we had is that we started with the food chain because we did this in XNA, and it was a big project with a lot of quests where each quest was a pedagogical objective. It was the first system took us a year, and the second system another year. But the problem is that the food chain is taught only in 90 minutes in 6th grade, and they don't see it much more. So you make a huge effort for 90 minutes, and the teacher has to learn how to use something for 90 minutes. So you have to think twice what type of software you're going to do when you know how much they're going to use it in school. That's our first learning. The second learning was that making such a game is really not easy. And those were the rules that we came through from our experience when we developed this game. We did this with Jan Plus of NYU, and it's published in Computer Education, so I'm not going through this, but if somebody wants, just send me a mail, and I will send you the paper, because they're really good guides on how to develop such a game. Together with that game, we did the electric charges game. This was the first version of the electric charges game, where you had 9 kids working together, but really they were in group of 3. So you have the group of reds, that's 2 of them, I don't see the third one. The greens, this is 1, 2, and this is the third one. And the blue ones, this is 1, 2, and 3. So they had to move. Between them, they were charged, so to move the different charges. Each of them had a charge. This is the green charge, the red charge, and the blue charge. So there were really 3 groups sharing one big screen. And what we discovered, that it was much more efficient to have the groups each with its own small screen than sharing this big screen. So if you're going to have a big screen, use it for doing really a work where all of them are collaborating, as the one we did with this classroom multiplayer presential game. Then we moved to 1 to 49. In 1 to 49, things get much more complicated. Here you have an empty room with the mouse already preset. Our experience is that the setup is so high that it's very desirable to have a classroom which is a lab for the 1 mouse per child, because setting this up is a huge problem. It would be nice, and we were talking with Donald, how to get rid of the mice, and with cameras it could be a good idea to follow. This work was done in India. You were in one of the schools. You went there, yeah? This was done in one of the schools in India. This is photographed in Santiago. This is a photograph in Costa Rica, where we were late November, early December. This is in Brazil, where we were in September. And this is in India. You might recognize these children. Kentaro gave us a school, and we were there a couple of times, if I'm not wrong, doing some work with these kids. The things we did, and this is a film shooted in India, where you see that each child is working at their own pace with their own nano window. What do we do in this nano window? In this nano window, basically, we allow each kid to work at their own pace. That means that you have an intelligent tutoring system, a rule-based system, that allows the kids to work interactively with the system and advance at their own needs. And since the system has persistence, once the lesson is finished, the system saves the state, so that in the next lesson, the child continues where he was. Here you have the feedback for the teacher, where the teacher knows where the different kids are, and the feedback that each child receives is the following. He did it right, he did it wrong, he finished one of the rules, this kid is sleeping, that means that for at least a minute he has done anything, and this kid is in deep sleep, that means that in the last 3 minutes he hasn't done anything, so that the teacher knows where he should address his attention. On the other side, if the teacher doesn't know the name of a kid, he just clicks here and the name of the kids appear. What we did, we compared the 1 mouse per child with a system where we use exactly the same engine, but we did an interface for a netbook and compared the netbook with the 1 mouse per child, and we also did it with paper and pencil in 15 sessions of 45 minutes each once a week. And the results are very interesting. What you see here is the percentage of students that achieved a given level. So you see, for example, that the kids that work with paper did much more exercises than the kids that were working with the netbook or the interpersonal computer, the 1 mouse per child. And why is this? Because these kids cannot advance at their own pace. These kids advance at the pace of the feedback. That means that the system don't allow us to continue to the next exercise if they have not achieved really that level. While these kids are working with paper and pencil. And the problem with paper and pencil is that you decide how good you are. There should be a teacher that supervises it. But
this isn't test performance. This is just how many exercises they got.
Yeah, that's just how many exercises they got. And we were a little afraid because we saw that these kids were doing much faster. And we saw that they were learning much faster. However, the learning was not so. Even the groups were formed randomly. The paper and pencil had a pretest much higher, but the improvement was much, much, much lower in the 3 groups. And what's interesting, that the interpersonal computer and the netbook were similar. There was no significant difference here. So what happens here is that we see that for these kids, there was no real difference. Now, what I'm trying to do now, for me, the next step is to show, not in small scale, but in a big scale, I would say 100 schools, to show that this type of technology really makes a difference. Because it's not only about the technology, as I'm going to show you later, it's about also how you transfer the technology. So what we need now is independent assessment and see really how you can make this work in 100 schools and how much do they learn compared with a randomized experiment in a real environment. It's not now 1 school, 5 schools, we really have to go to a much bigger number of schools. We have done this for the arithmetics and for fractions. Here you have, for example, a representation which is number and have to construct the number. What I didn't mention, which is very important, and we didn't realize until last year, that what's really very important here is that the children construct the answer. It's not a multiple choice question, but they really have to construct it. They cannot guess it. So there's no way of guessing. They really have to learn what the correct answer is until they really get it. And if it's red, 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 then comes the teacher and explain them, and they advance and really get the point. So you have a number representation and a number solution, or a graphic representation, a graphic solution, graphic representation, number solution, or you can even have words. So you see that even in such a small screen, you can get a lot of different ways of doing things. For example, Kentaro is sitting in the back, and I don't think you have problems in reading this. And what we have seen, that the focus of attention of the kids is really perfect. You can see this, especially in the photograph of here, of Costa Rica. Look that the kids are looking to different spaces in the screen, because each of them are looking to their own box. Yeah, but they really focus their attention to their own screen. Look how she's counting. And the last thing, which we're just now finishing, is we're doing decimals. So you have now, for example, a decimal representation. You can also have graphics, for example, here, which is bigger, the green or the yellow. So here appears bigger, equal, or less. So in this way, what we have achieved, that we have math for 1st to 6th grade. I wouldn't use this for 1st graders. I would start with 2nd graders, because I'm not sure if their 1st grades are really mature for such a system. Last year, we got a grant from Microsoft and Laxir, where we introduced games. And the games we did, I would say, are not as mature as I would say this is for really doing a big scale. I think we have to do a 2nd iteration there. We're doing a 2nd iteration. These were more edutainment games and real games where we have more rules related to what the kids have to do. Here, for example, they're building a bridge. Here they have to collect chickens, collect fishes, or they have to, darts. The problem here, more than the games, is that there are multiple choice type of problems. And we discovered that the kids began to guess. Here we saw the real importance of constructing the answer. So now we're doing a second generation where we have different type of games, and the kids have to construct the solution. And we're going to test this year. Here you see how it looks like. This is a real photograph where you have all the kids playing the different games. Then we saw that with this type of infrastructure, you can have a super clicker, which we named the Augmented Clicker. In the Augmented Clicker, as in the clicker, you have a question and you have alternatives. But instead that the answer corresponds to the whole classroom, now you can know exactly what each kid did. So in this case, you know that this kid was wrong, this kid was right, and you can also have a complete view of the whole classroom, how they're doing. So I would say this is a synchronous interactive system with much more detailed information as a regular clicker with a very simple infrastructure, just one mouse per child. And then we have the super clicker, which is an asynchronous clicker, because this is synchronous, that is all the children have to work at the same pace. And here's an asynchronous one, where each child works at its own pace. What we give them is a guide of two guides of paper sheets. In one of the guides, you have the questions, and in the other guide, you have the feedback. So since the kids have to work at their own pace, we have two states. First, the kid has to look to the question. So answer. He looks basically to the question with the corresponding answer, so he has to answer the question, and here he has to first confirm that he is effectively in question number 1. So he's in question number 1, and we're saying that the first letter of the first word starts with EE. So he can choose different ones until, for example, this is the first one, EE or DU or QU. So he can select one, and if he's not right, the system will say, hey, take care. This is not the right question. Look to your right question. So we are sure that he's in question number 1. So once he confirms that he's in question number 1, he has to respond. Once he responds, so he confirmed, and then he goes to response. And when he responds, he can be right or wrong. And if he's wrong, we give him feedback. And we send him to the corresponding feedback. And in the feedback, he also has to confirm, for example, where is feedback? He has feedback 53. He has to confirm that it starts with a given word so that we know that he's reading the corresponding feedback. What's very interesting is that what we saw is that the kids, this is the time that the kids took for questions, for reading question and answers, and this is the time that the kids took for the feedback. Look, the curves begin to separate after 6 seconds. And what we saw is, if the two kids took more than 6 seconds for reading the feedback, 71% of the answers were correct. But if they took less than 6 seconds, 37% of the answers were correct. That means that the kids that really read the feedback learned more than the other ones. And the feedback really helped the kids to learn more. Then we said, how can we collaborate in a big classroom? Because we started with collaboration and we moved into interaction, but we really wanted a collaborative classroom. How do we get a collaborative classroom? So what we did here, you don't have 49 kids. Here you have 20 kids. Here you have a double entry table where you have, in this case, the parts of a phrase, and here you have the different letters. And each kid belongs a letter. For example, the kid, this green drop of water, is cheap. So where is he? He belongs, he owns cheap. He belongs this. So look, he belongs this. This should be an adjective that starts with DEF. Is this right? No, this is not right, because it doesn't start with DEF, it starts with C. But here's somebody that's telling him, I want to exchange your word with mine, which is invention. So this guy wants to exchange this word with this other word. However, cheap is not a preposition. So if they do the exchange, it would be wrong. If they make the exchange and it's wrong, they lose 2 points. If they make the exchange and it's right, they win 2 points. And you see it here. Kids that have negative numbers and kids that have positive numbers. So they cannot make exchanges if they have both to be sure and both have to agree. If both agree and they make the exchange, for example, he agreed, and now if he accepts, then they would lose the points. And what we saw here, that they get this language, is called the silent collaboration language. Why silent collaboration? Because look, there are 20 kids here, there are 20 kids here, and there are another 20 kids here. These are looking to this projector, and the other one are looking to the other projector. And the kids have to collaborate with peers which are not side by side. And what happened, that they began to shout. You see how he's shouting? He's shouting something, hey, I need your word, please give me that. So this was a little loud, yeah? So we said, how can we do something different which is not as loud as that? And this is the newest work we have done. I don't know if you know Ton de Jong. You know Ton de Jong? He's a researcher from Holland. He sent me one of his master students who worked with us and one of my PhD students. And what we did is the following. Now you have the whole classroom, and you divide the screen by 4. So in this case, you can have 9 or up to 10 kids in one of these squares. So this is one group, this is another group, and so on. And the teacher supervises all the groups. What they have to do, they have to construct a triangle with 2 sides that are the same. So initially, the points are random, and each kid belongs a point, a vertex. And what they have here is a polygon, which is not a triangle. So the teacher says, you have to build a triangle. How do you build a triangle? So the kids, the first time, have to find out that they have to collapse the vertices until they reach 3 vertices, and then they have a triangle. And the feedback, the immediate feedback, is this face. This face is not happy, and this face is extremely happy, and it finished, we say, okay. So the face begins to move. You see how the face is beginning to move at the time that they're getting closer and closer to the answer. So what they're doing, they are constructing collaboratively, and really collaboratively, because each kid is accountable of one of the vertex. And what one kid does relates to the work of all the group. So what we saw is things like, for example, that this kid says, hey, you have to move. And if he doesn't move, he goes here, comes and begins to do something like this over this, saying, come here, come here, come here. So the kids began to help each other in a silent way. And we really saw that here, the shouting, there was some shouting, but much, much less than the other. Now I have a master student where we want to see how we can do this type of work, but not only for geometry, where it's explicit that you can do things like that, but now for language and also for math. And the last topic is, okay, we have done so much software, pedagogical software. However, teachers don't use this software. While we are there, they use it. But the day we leave the school and left them alone, they stop using it. And with Pierre Dillenburg and Jeremy Rochelle, we are working something that now we are talking about orchestration. And the idea of orchestration comes from the following. There's a deep problem behind. With the multi-mouse, we saw this explicitly in not one classroom, in not in one city. We have seen this in Argentina, in Brazil, in Costa Rica, and in Chile. What happens is that we are in 4th grade, for example, and the teacher has to teach a given subject because the curriculum says he has to teach the subject. However, if you look to the kids, and you can see exactly where the kids are, you will see that in one same classroom, you have kids that still don't know how to add numbers with 4 digits. You see kids that don't know how to subtract numbers. kids that are beginning to multiply. Some kids now know how to divide, and very few kids are close to where the teacher really is. But the teacher don't care, because the teacher has to follow the curriculum. So the teacher is teaching to almost nobody. He's teaching what he has to teach, and he really doesn't care, or he cannot really follow the pace of the other children. So what we say is that we have to support these children while you also lecture. So you have to orchestrate the classroom in such a way that sometime you give it for the kids to come closer to your needs, and while you teach this, you have to complement what you're teaching with what you know your kids are. So orchestration is to give the teacher a general strategy of how you're going to follow the curricula, how you're going to script each of the classrooms, and how you integrate conventional digital resources. This is, of course, just a guide for the teacher, and the teacher will see how he's going to use it. However, you really structure the classroom in such a way that the teacher has an idea on how to improve what he's doing using technology. The way we orchestrate the lecture is the following one. We address the three different moments of the classroom: the opening phase, the instructional phase, and the closing phase. And the activities we give them are first indication about how to organize the students, what type of questions have to be asked the students, and the answers he can expect, and how to really react to these answers, what activities he should do, and how really the children should do these activities, how to integrate the digital and non-digital resources, how to do formative assessment every moment so to know the state of the kids, and finally, what's very important, how to schedule all this so that the time assigned to each activity is respected so that he can really do all this. And the resources that we give him, we not only give him technology, we also give him paper guides, interactive guides for PowerPoint presentations, with or without audiovisual support, individual or group work with or without technological support, participatory interactive activities, homework. What we're doing now, we started just this, we're going to start it now. We have the activities for the one mouse per child, for the netbook, and now we also have it for the web. And the idea is that the kids can do homework, and that this homework is synchronized with what they do at the classroom. So the system saves the state, and the system automatically gives them homework with some rules behind so that he can advance much faster with his homework. So that's it. That's what I've done in the last couple of years.
Great. So we have a few people here in the room. I suspect a lot of us are remote, and I don't know how to get your questions. But I'm going to open up a little bit of Q&A because we have some time here if anyone wants to ask some questions. And Miguel. Well, yes.
So I have one question about so when you're looking at the conditions of the using like for the math problems, the combined multi-mouse situation versus the netbook versus the paper pencil, and you saw the marked improvements between the electronic versions and the paper one. And your concern and your observation was that with the paper ones, the students would just kind of go along at their own pace, but they wouldn't really be self-checking. So I wonder, is there anything you could do even with the paper though, to make it a little bit more evaluative? So like, if like maybe after they finish it, they have to turn it over and look at the answer.
Yes, we did this. What we did is, the paper guide was made in such a way that they had like 10 or 20 exercises, and then came automatically the answer guide.
Oh, I see.
So that they had to look back and see what were wrong. But the problem was that it was wrong, and it was wrong, and they go forward. It was wrong. I didn't do it again. So, but the point here that the teacher should be much more active. So the teacher should go to the guy and say, hey, you have so many wrong, you should all do this again. Right. But the kid would say, hey, but I already did it, I don't have a place where to do it again. Yeah. But on the other side, when it's electronic, if it's wrong, it's wrong. You cannot go further until you get it.
And the problems that the different kids, adjacent kids had were different enough so that they couldn't copy?
No, there wasn't a copy, because that's the teacher looks. Hey, you're copying, you shouldn't be copying. That's something the teachers know. They shouldn't be copying. No, that was not the problem. The problem was that when the feedback came, the kids knew that it's wrong. Okay, it's wrong. But what I do is it's wrong. And we said to the teacher, please, because we saw that problem, and tell him, but when it's wrong, please do it again. And the teacher said, yes, do it again. But this was not really mandatory.
Yeah, yeah. Interesting.
Anyone else?
Have you asked the teachers why they don't use the games when, after you remove them?
And Miguel, can you repeat the question?
Yes. If we have asked the teachers why they're not using the technology once we leave, I would say one of the problems was the setup. Definitely it was the setup. And the second problem was the guidance. That's why we are so concerned about the guidance. Because when we were there, we didn't go all the weeks. We went every 2 weeks normally in this project, the last one. But we tell them what to do. And after we leave, there was no guidance. So they felt very lonely. And I would say they're not confident enough with the technology. They feel that what happens if they're not here? Who can help me? So that if I don't use it, nothing will happen. So better, it's less cumbersome for me not using it. And that's why I think that if we structure everything and that we really help them to show them the way, what to do, what type of question, and everything is not, it's really nicely done, because it's very important how you present all this information. It cannot be information overloaded. It's very simple so that teacher can really fast use all this. We believe that you can make a difference. And this year we will have an experiment where we will have teachers with this orchestration and teachers without this orchestration to see, and let them alone, just with orchestration, and see what happens. So we really want to see what happens with a good orchestration. And we're investing a lot of effort in doing a very good orchestration.
Can you talk a little bit about your vision for the one mouse per child? I came in a little late, so I'm not...
Vision in what sense?
Well, just vision of where do you expect this to go in terms of, I mean, you just mentioned...
Where to go? I would say there are two worlds, the rich world and the poor world. In the rich world, where we are here, for example, I was yesterday at SRI, and in SRI they have a very nice new machine, which is as big as this one, with a projector. It's a computer that has a small projector that can project something like this surface, and with good light. It costs $350, and each kid with his own mouse. And since this computer and projector is so small, you put it over the table with a plain piece of paper, and you have a really ubiquitous computer. And since this is also Wi-Fi, the teacher can know exactly what's going on. So I would say this is, for me, as ubiquitous as it can get with today's technology. I think this is a very nice frame for doing small group collaboration in the classroom. And as showed you here, there's a lot of things you can do with small group collaboration, with this sharing, with more than one mouse per child. Is the interpersonal computer. Yeah, Dylan Book named this the interpersonal computer, because there's one computer for all these kids. I would say I personally think this is more not only affordable, but more versatile. Versatile, you say it? Versatile? Versatile than giving each kid a tablet. Yeah, because a tablet is more cumbersome. What we saw with the pocket PCs, they don't really share the information. In the interpersonal computer, they really share the information, and you can do almost everything there. Of course, the pedagogical design is not obvious. You have to really do a good instructional design, but you can do a lot of things there, as I showed you in this presentation. And then comes the other world, the poor world. In the world of the poor, I would say, I remember when I came to Kentaro with the 1, 2, 3. And you say, this is very nice, but it doesn't solve my problem, you told me. And we need a solution for 50 kids. You remember when I first visited you in Bangalore? And so I came the next year with the 1 to 49. And here, today, a computer, you need not more than a double core. A double core with 2 gigs of memory costs today $350. And then you need a projector, a VGA projector, which costs today $350. So you have $700. And the mouse, and perhaps we could do even with cameras, but today with mouse, the mouse for 50 kids, it's another, and the hubs, another $300. So it's $1,000. So it's not anymore the cost of technology, because the kids are not going to use it the whole day. So the kids will use it at most once a day, at most. So a group of kids can share this if they're inside the lab. So if you make the cost per kid, it's around $1 per day, per year, $1 per kid per year. So it's not anymore the cost of the machines. It's now really how do you introduce something like this in a school and that the school really make a good usage of it. So I would say that's the problem now. The problem is not the cost of technology. The problem is now how we change what's going on inside the school. Do you agree with me?
I would say there's also the cost of maintenance and support, which often ends up being in multiples of the hardware costs.
Yeah.
But the good thing is only one computer.
I agree. So there's some things, but otherwise, I think this is certainly the way into having multiple kids interact with computing.
And the other thing which is good is it's only one computer, which the kids are really not having touch with the computer. So the possibility of putting viruses inside, it's much, much, much smaller.
What about the factor of kids enjoying learning in this way as opposed to a more traditional way? Is there a way to measure that, or just enjoyment that you see in the classroom? Or?
I would say more than enjoyment, what really drives me is since 1995, when I started working with technology in the classroom, is that I cannot believe that in 2012 now, I said this in 1995, kids of today are completely passive in the classroom. Because the teacher is the main actor. As here, I am the main actor, and you're completely passive. And the kids, we're in a generation where the kids are really very interactive and very graphic. The classroom, everything is passive and words, just words. So we really need to change this classroom to a classroom where the kid is the first person actor, and we need a teacher. I definitely do believe in the teacher. I always have mentioned the teacher in my presentation because the teacher is the mediator. The teacher is the one that knows where to go and knows who to help at each moment. I need a teacher that's very active in the classroom and moves in the classroom to see where he can really act and help those kids. So I see more than being happy inside the classroom, I would say being engaged in the classroom, engaged in learning. And of course, if we can do it with games, why not? Of course. You saw that I'm studying how to introduce games. But the point here is the engagement, that the child is really responsible of his own learning. That's the main point. Because today the kids are not responsible. Nobody makes them accountable, even more. If we go back here, how can the kids be accountable of their learning if he's teaching this and he knows that all these kids didn't understand anything of what he's explaining? However, he has to teach it because the system asks him to teach that, and that happens worldwide.
Do you ever worry about, so one thing I would be concerned, so imagine a system that was like the math system that you showed, 50 kids up in the grid, they're doing stuff, and the system realizes this kid is not doing so well on multiplying large numbers, so it goes down to multiplying small numbers, he's not doing so well with that, it goes down to adding small numbers and so forth. Do you worry at all about the embarrassment maybe that a child might feel because he's kind of up there in front of all his peers can see like, oh, that's this guy, and he's
no, we haven't seen that, and we were in three different. We were in urban and rural schools in Chile, Brazil, and Costa Rica, and we really didn't notice that. We worked with small kids, third grade. We haven't worked with older kids, but it hasn't been a problem. No, it has not.
Maybe they're engaged enough in their own tasks they don't.
I would say if you look to this photograph is so nice. I hope it's not so far away. Should come soon. This is a perfect picture. Yeah, look how they're looking to the small screens. You see, everyone is looking to a different place because everybody's looking to their own screen.
Except for the one in the middle who's counting her fingers.
Yeah, she has to have some support.
Sometimes the oldest
A little
tools
bit
are
of
the
help.
best. Yeah.
But she's doing support.
I think, yeah.
So I just want to say one thing on the question of the future vision, just from the perspective of MSR and the potential that we see. We've talked to Miguel. I mean, definitely the idea of using cameras or Kinect ceiling mounted, something where we could track students' hands and bring this at a lot less invasive input into a multi-mouse system is really exciting. But as you mentioned, not here yet.
Not here yet, but it doesn't look so far.
It's not so far, and I think there's a lot of existing work around tracking this kind of stuff that can be done with simple machine vision. But in terms of the environment, the platform, really, I mean, the way we envision this is as one mouse per child as a platform, where you can think of this providing an ecosystem, trying to build up an ecosystem where a multiplicity of partners could create little apps that fit inside this form factor, one on top of another, that use the same kinds of iconography, a common language of the iconography plus the control sets, so that it's easy for teachers and students to like just dive into this. And thinking about adaptive learning on an even larger scale, where students can be working at different levels within the current system, but what if when a student is finished with their work inside of one topic, they can actually go to work in another topic. Or even when talking about working with teaching to the top end of the class or to the middle third, or however the teacher decides to strategize, say they're teaching to the middle third, those students that are ahead of the curve, who've already finished all their stuff, they start to get bored. And part of the teacher's job is to try to keep them occupied. And you could give them additional assignments or things like that. But you could even do something, if you think about games for learning, what if we just give them games? Not even meaning to be educational games, but simply as some kind of reward, where you can say that they can, those kids can play a little Drop 7 or Farmville or whatever the heck it is that amuses them, and it keeps them occupied and also acts as sort of an extrinsic motivation and incentive for the other kids to get finished, to get some kind of reward.
Sorry to interrupt. I would say the secret is this: to find out games where the rules of the game are intrinsic pedagogical rules. This is the secret. That this is a game, very engaging game, but it's Coulomb's law. Who could believe that the people want to play Coulomb's law?
Well, but at the same time, I guess I'm a little bit skeptical about that claim, because if you think about first-person shooter, like, it's based on physics, but you're not really learning physics by playing the shooter. Even though the mechanism of control is Coulomb's law, like, they're learning that, if I move this guy close to this, then he moves further away, and if I move this one and this other negative one, then it gets closer, and things like that. So they're learning kind of how to control, which is fun. And I would agree that they're gaining intuition, for how electrical fields are working, but
you need
the mathematics.
it's not everything
Like
there.
exponential drop.
Yeah, it's not everything there, of course. That's why I said you have to integrate. It's not only the digital. I said it. You have to have other resources too.
I think it's key.
I mentioned that at the end.
And I think there's other ways we can wrap this. I mean, we talk a lot about frame games, wrapping games around core educational experiences, but you could almost imagine wrapping education around a core game experience with this. For example, if you have, say, 20 students who have their little one mouse per child context around a shared window where they're catching fish or building a castle or engaging in some cooperative play, where every time they complete one of their little drill assignments, it's filling in this picture or filling in pictures of a puzzle. So you create that sort of magic circle of gaming around something that you don't have to worry about, because I agree with you. Transfer is a huge question, and with traditional edutainment, it is the problem. But what if we just have them work and we put the game in a separate context so that the two don't, why do we have to blend them together all the time? But anyhow, thank you everybody for coming out, and I hope this was entertaining and enlightening. Just in terms of our next steps, we're looking to try to help Miguel to scale this thing out. We want to go to 100 schools in Costa Rica next year. That's at least the near-term goal. So anyone out there watching this, if you think you can help, let us know. And thanks a lot.